Welcome back to the channel. Today, we're diving into one of the most important topics in high-performance home building: how to design HVAC systems for homes with very low heating and cooling loads. This design direction is from the U.S. Department of Energy based on Zero Energy Ready Home. They're designed to deliver all the benefits of a zero-energy home, right from the start. It is clear that as homes get tighter and better insulated, the old rules of HVAC design don't apply anymore. Loads drop dramatically, but comfort becomes harder to get right. So what's the number one rule of HVAC design in these homes? The most critical principle for low-load HVAC design success is keep velocity up and mix to ensure proper air distribution and comfort. In other words, comfort is no longer about how big the equipment is. It's about how well the air is moved and mixed throughout the space. Traditional low-velocity systems just don't cut it. Instead, we need higher velocity, about 800 to 900 feet per minute, to throw the air across the room and keep temperatures even. Efficiency doesn't automatically mean comfort. In fact, the most common complaints in high-performance homes aren't about energy bills. They're about drafts, uneven temperatures, and stratification. That's why following the fundamentals in a CCA Manual J for load calculations, Manual S for equipment selection, Manual D for duct design, and especially Manual T for air distribution is critical. Think about this. What is the major comfort issue in traditional home? Major comfort issues include stratification, temperature layering, air movement, drafts, and room-to-room temperature variations. In older HVAC designs, you might accept a few degrees of difference between upstairs and downstairs. Industry standards allow +2 degrees Fahrenheit variation in heating and +3 degrees Fahrenheit in cooling between rooms. These temperature variation standards date back to the 1930s-40s and may not reflect current occupant preferences. But in a zero-energy ready home, small comfort issues stand out more. People notice when their head feels warm but their feet are cold. And while modern windows and insulation solve a lot of radiant temperature problems, air movement and mixing are the big challenges left. One of the strongest messages is HVAC can't be an afterthought anymore. It has to be part of the architectural design process from day one. That means planning space for ducts, equipment, and registers, terminal units, just like you plan space for a kitchen or a bathroom in the design phase. Done right, a modern HVAC system is quiet, efficient, and almost invisible. You don't notice it working, you just feel comfortable. The builder, architect or designer, and HVAC contractor should coordinate the location of HVAC equipment and ducting prior to finalizing construction drawings, with the goal of minimizing the total effective length, telephone, of the duct system. Telephone equals linear feet of duct plus equivalent length of duct fittings. Load calculations can be manipulated to make oversized equipment appear to be correctly sized. HVAC systems operate at peak loads for less than 1% of annual hours but at partial loads for thousands of hours. Designing for intermediate conditions rather than peak conditions may improve overall system performance. Building America has developed guidance documents for load calculations, equipment sizing, and air distribution. Room-by-room CFM requirements often differ significantly between heating and cooling modes, requiring careful balancing. Another takeaway: most systems today are oversized. The truth is, peak load only happens for a tiny fraction of the year. For the other 95% of the time, your equipment is running at partial load. System sizes have decreased dramatically from 400 square feet ton to over 3,000 square feet ton in high-performance homes. So instead of sizing for the absolute hottest or coldest hour, it may make more sense to size slightly smaller, so the system runs longer, mixes better, and delivers more consistent comfort year-round. With smaller systems comes less total airflow, making proper distribution more critical. Register selection also matters a lot more than people think. The experts showed that high sidewall supply registers on interior walls work well for both heating and cooling climates. Throw distance is more important than spread for effective air distribution in high-performance homes. Higher air velocity, 800,900 feet per minute, provides much better room mixing than traditional velocities, 400 feet per minute. At low airflows, 3050 CFM, most residential registers are oversized, leading to poor performance. Register selection must be matched to the specific airflow and throw requirements of each room. The DOE-CFD simulations confirm that higher velocity air delivery creates better room mixing in both heating and cooling modes. Low velocity systems allow warm air to stratify at the ceiling in heating mode. In cooling mode, low velocity systems allow cool air to pool at the floor without proper mixing. Thermostats may be satisfied before the entire room reaches the desired temperature with poor mixing. Air velocity is more important for comfort than the absolute temperature of the delivered air. Compact duct system. Another strategy is compact duct design. Compact duct systems with consistent duct lengths provide more uniform air delivery temperatures. Low-mass duct systems, flex duct, ductboard, show much less temperature variation between registers than all-metal systems. Temperature differential across registers can cause comfort issues even with correct airflow. Shorter duct runs allow higher velocities without excessive static pressure. Rooms nearest the thermostat often receive the warmest, coolest air, potentially leading to improper cycling. For compact duct design, follow these duct and equipment layout and grill selection. Equipment placement. Locate furnace or heat pump air handler as close to the center of the house as possible. Supply grill placement. Locate supply grills close to interior walls of rooms where possible. Side wall registers are preferred. Grill selection. Select supply grills that provide sufficient throw to reach exterior walls. Air supply considerations. Avoid supplying air to low-load interior spaces such as closets and powder rooms. Duct and equipment sizing. Load calculation. Use ACCA Manual J to calculate loads using the 0.06, 0.06 CFM per square foot. Supply, return leakage assumption. Leakage class 153. The appropriate insulation, R8 for attic ducts, and the 7CA duct location option. Equipment sizing. Size equipment in accordance with Manual J and the Energy Star HVAC System Quality Installation Checklist. Duct sizing. Use a CCA Manual D to size ducts based on Manual J loads. Duct installation. Sealing. Tightly seal all duct connections and joints with mastic and test to confirm a leakage rate of not more than 5% of total system airflow. Flex duct installation. Stretch flex ducts out to full length and avoid kinks and compression. Duct location. Install ducts in conditioned space, either in an insulated non-vented attic or crawl space or buried in attic insulation. So what's the bottom line? Select equipment that actually matches the smaller loads. Use higher velocity duct design, 500 to 900 feet per minute, not 300. Plan HVAC layouts from the start of the design process. Pay attention to register placement and selection. And remember, efficiency is great, but comfort comes from air distribution and mixing. The future of HVAC in zero-energy ready homes isn't just about making systems smaller. It's about making them smarter, better integrated, and designed around human comfort. So if you're a builder, designer, or HVAC contractor, the message is clear. Rethink the old rules. Smaller loads don't mean HVAC matters less, it means it matters more. Thanks for watching. If you found this helpful, hit like, subscribe, and drop a comment below. Would you rather live in a home with ultra-low energy bills, or one with absolute comfort, even if the bills are a little higher? Let's hear your thoughts.